strand held together by hundreds of thousands of hydrogen bonds. But rather than just being a solid crystal, those Lego-like regions are strung together by the highly elastic regions, allowing the protein to bend back on itself and knot together into a solid fiber composed of many thousands of individual strands. And because each individual fiber is quite long and has many crystalline domains, it can connect with dozens of different proteins in multiple spots, tying them all together tightly. The other subunits that I used are the beta spiral region from flag silk, and two regions from piriform silk which I noted as the proline-rich and glutamine-rich subunits. The flag section should add more elasticity, and the piriform regions could make the fibers slightly sticky, though it's unclear from the literature if these subunits are what actually makes those proteins sticky. Instead, one of the reasons I chose piriform silk is that fiber for fiber, it's almost as strong as major ampulate silk, but can take more strain. So I can get the randomness I want without compromising its material properties too much. By mixing and matching these, I should be left with a protein which mostly maintains the strength of MASP1 while actually having a little bit more elasticity. When we talk about the strength of a material, there's two things that we normally measure: stress and strain. Stress is how much load the material can actually take, and strain is how far the material will deform before it breaks. Toughness is the combination of the two. MASP1 can take more stress, that is more load, but less strain, because it's not very stretchy. Whereas the other silks can take more strain, but less stress. That is to say that they'll stretch more before they break, but it takes less force to do so. It's kind of the difference between a steel cable and a rubber band. One can hold a lot of weight, while one can stretch a lot. Silk is like what happens when you mix the two and make stretchy steel. And that's not really a figure of speech. Spider silk can take both more stress and strain than most steels, and outperform most common materials like cellulose, nylon, and other plastics. So considering that, I'm actually quite comfortable trading a bit of stress tolerance for more strain tolerance, and should still end up with very strong fiber. And some of the other features I added that we'll talk about in a bit should actually compensate and raise the stress tolerance above even natural silk if I'm lucky. With these 5 subunits in hand, I'd make multiple versions of each so that when I string them together into a gene, it still doesn't get too repetitive. One of the nice things that help with this is that DNA is broken into codons. These are 3-letter codes that tell the ribosomes which amino acid to stick onto the protein next as it's being synthesized, and there can be multiple codons for each amino acid. For example, in the gene, if there's a GCT, GCC, or GCA, all of these get read and an alanine amino acid is added regardless of which one of these is present. So, after going through all the subunits to figure out which amino acids I need for each, I made a chart of all the different codons that are possible for each amino acid. And I removed any which aren't used in the species of yeast that I plan on using. While a codon table like this makes it seem like any codon can be used for any amino acid, that's not accurate, and not all organisms use the same codons, and each tend to prefer specific ones over others. So using the alanine example from before, some organisms may vastly prefer GCT over GCC. So it wouldn't make sense to use a codon that an organism lacks the machinery to use properly. Those preferences are hard-coded into the chemistry of the organism, so trying to use a codon that the organism lacks the machinery for can ruin the protein and have it in check before it's finished being synthesized. With that done, I had a table that I can start building with. For each subunit, I figured out how many of each amino acid I would need, and then used a random number generator to produce strings of numbers from 1 to however many codons I had available for each instance of the amino acid present in each subunit. I realize that sounds convoluted, so let's see one example. I'm going to use the glutamine-rich subunit because it's nice and short. The amino acid sequence is QQSSVA, where Q stands for glutamine, S is serine, V is valine, and A is alanine. So I need 2 glutamine codons, and I have 2 to choose from. So I had the random number generator spit out 20 pairs of 1s and 2s. So either a 1-1, a 1-2, 2-1, or 2-2 randomly. Then I did the same thing for the other aminos and strung them together in the proper order. But to make it clearer, when I moved on to the next type of amino acid, I'd shift the numbers. So for serines, I'd use 3, 4s, and 5s, the valines 6s and 7s, and alanines 8s, 9s, and 0s. If this is my newly randomized sequence, I would then take that string of numbers and go back in and replace them with the appropriate codons for my list. So a 1-1 would become CAG, CAG, 1,2 would become CAG, CAA, and so on. This was repeated until I had 20 versions of a DNA sequence that would all code for that same QQSSBA amino acid sequence. Once I had repeated this for all 5 subunits, I had a list I could work with. The only one I didn't make 20 versions of was the protein-rich region because it was just so repetitive. But now the big question is, how do I mix and match these? Do I try and keep the same order as the source silk, or do I do it totally randomly, or do I try and eyeball it? One of the saving graces at this point is that when you look at the various types of silk, there's actually a fair bit of variability in how the subunits go together. For example, there's a lot more elastic regions between the usual crystalline regions in MASP2, yet the protein remains quite strong. So as long as I have large quantities of the crystalline region with stretchy stuff in between, it should be fun. So I started generating randomized variants until I found one that looked right. There's a story about how the SR-71 was designed, where one of the lead designers brought the designs home to his wife, and she would say if it looked fast enough. That was basically what I did with this. I just kept messing with it until I found spacings of things that looked good to my eye, and it looked silky enough. And honestly, it doesn't actually matter that much. This is just the starting point. If the end fibers have garbage properties, I can always generate a new version that more closely resembles the source protein and have that printed. Maybe using less of the piriform or flag subunits and more of the major ampulate ones. But this will give something as a baseline to work with and should have most of the properties I want, as I did try really hard to have it resemble the real thing. And this costs so much less to do, so generating a new version, while a bit tedious, is fairly easy. Every time I generated a string of numbers like this, I would go back in and replace each one with the next random sequence in my subunit list accordingly. So the first time I hit a 1, I'd use the first sequence from my crystalline list, and the next time I'd use the second one, and so on. And once all the numbers were replaced with DNA sequences, I checked the resulting DNA and protein using some online tools to see how the protein itself looked visually and see if it seemed synthesizable. I use a company called Gene Universal for all my gene synthesis needs because they're fantastic. And they have a few different DNA backbones in stock to choose from that work in yeast. You can think of the DNA backbone as sort of a blank CD which can be loaded with whatever file you want, which in my case is the new silk gene. I ended up picking one called PPIC9K because it had a bunch of features that I wanted. First, it obviously works in yeast, which is what I wanted, not just because saying spider beer is fun, but because yeast are much better at producing big proteins like this in large quantities, and so are better for large-scale stuff. Next, it uses G418 to select for the modified yeast. G418 is an antibiotic and is cheap, easy to use, and frankly, I already have lots of it. So it makes isolating yeast cells which have taken in the new DNA after we modify them very easy. Next, it's an integrating plasmid, which means that when I put the DNA into the yeast, it'll work only if the DNA integrates itself into the yeast core genome. This makes the mod permanent and means that once I've got the finished yeast, I can grow them without needing to keep adding G418 to the growth media, making it much cheaper to grow them in bulk. Think of this like updating the yeast operating system rather than installing a self-contained program. And finally, it contains a special tag which is added to the front of the silk gene that causes any silk produced to be excreted by the yeast into the media they're growing. This means I won't need to worry about collecting the yeast and popping them open to get the silk. I can just harvest the growth media to collect it. Also, this reduces the burden on the yeast, as without it, it would literally fill with silk until they clog up and explode. So each individual cell can actually produce more silk protein before they eventually die. But before we sent off the finished construct to the company to be printed, there was one last thing I wanted to add because, screw it, project food for days. A field of study I'm fascinated by is biomineralization. Biomineralization at its simplest is the idea that various biological proteins can pull minerals, metals, and more out of a solution and solidify them into particles. This sounds strange, but if you think about it, is exactly what happens when bones grow or creatures grow a shell. Various researchers have narrowed down which proteins, and importantly, which very short pieces of said proteins are actually responsible for this mechanism for a variety of materials. These short protein fragments are called biomineralization peptides, and literally hundreds have been identified for a huge variety of minerals, metals, and other materials. I chose 4 peptides that should each bond to one of 4 different materials and strung them together with an inert spacer between them. This will give them a little bit of wiggle room so as to not damage their individual functions. This small chunk of biomineralization peptides was added to the very end of the silk gene, and then the whole plasmid was sent off to the company to be made. The reason I did this was because I wanted to make sure the silk had extra properties. For example, the first peptide, taken from oysters, should collect calcium onto the silk. If carbonate ions are also present, this will turn into calcium carbonate, which is basically how shell forms. In fact, this same peptide also binds to a molecule called chitosan, which is one of my all-time favorite materials. In theory, this should make the silk mineralize into a hard, tough material, very similar to mother of pearl if exposed to the right chemicals. But even without mineralizing, this should actually make the individual protein filaments stick together at their ends when calcium is present. This sort of artificially extends the length of an individual fiber by linking two together. One of the reasons natural silk is so strong is because the protein itself is actually really long, about 3,000 amino acids total. My protein is only about a third of that, so these mineralization peptides are one way of sort of cheating a longer protein into existence by binding two shorter ones together end to end. The other three peptides I added stick to silica, silver, and graphitic carbon materials like nanotubes and graphene. The silica peptide comes from diatoms, which are microscopic